Hello viewers, welcome to the next session on the stereochemistry of organic compounds. In our today's session, first we will review what we had discussed in our previous sessions. Then we shall move on to another type of stereoisomerism, that is optical isomerism, and we will talk about optical activity. Then we shall talk about the instrument called polarimeter that is used to measure the optical activity. We shall talk about chirality, enantiomers and racemic mixtures, and finally we will summarize our today's work. In our previous session, we had discussed that configurational isomerism, which is one type of stereoisomerism, can further be of two types. We have already discussed geometrical isomerism in our previous session. Today we shall talk about optical isomerism. What is optical isomerism? It is existence of two or more isomers of a substance that differ in their optical activity. What is optical activity? Optical activity is one of the physical properties. You have studied many physical properties about compounds like melting point, boiling point, density. Similarly, optical activity is also a physical property. It is the property of a molecule to rotate the plane of plane polarized light. Molecules which rotate the plane of plane polarized light are said to be optically active. But what is this plane polarized light? We are familiar with the light, that is we call it the ordinary light. It consists of oscillating electrical and magnetic fields, or we can say the waves vibrating in all directions perpendicular to the direction of the beam of light. Say this is the beam of light shown in the red line. Then these are different directions in which it is oscillating. On passing this ordinary light through a device called polarizer, its oscillations in all but one direction are blocked, and the light emerging from the polarizer oscillates in only one plane. We can show it like this. This is ordinary light, and when it is passed through a polarizer, now we have got its vibration in one plane only. This light is called plane polarized light. Plane polarized light we can show like this also, because each ray will have its two components, magnetic field and electrical field, and they are at 90 degree to each other. So, they oscillate in a plane, like this is the oscillating electrical field in this plane, then its magnetic field is in a plane which is perpendicular to it, shown in yellow color here, which is like in horizontal plane here. This is a vertical plane shown in this. So, this light which has got now two components, its electrical field and magnetic field. It is the electrical field that is more important, because these interact with the moving electrons in a molecule that causes rotation of this plane polarized light. So, this is ordinary light. When it is passed through a polarizer, we get plane polarized light. When this plane polarized light is passed through solution of any optical active substance, then we find that its plane has been rotated by some angle. Generally, this angle of rotation is represented by alpha. The substances those rotate the plane of plane polarized light to the right are called dextrorotatory, and those which rotate it in the left direction are called levorotatory. Means first, a compound, if it disturbs the plane of plane polarized light or rotates the plane of plane polarized light, is said to be optically active, and then optically active substance can be either dextrorotatory or levorotatory, depending upon in which direction it rotates the plane of plane polarized light. Dextrorotatory substances are represented by plus sign, or a small d is written before the name for that particular compound, and levorotatory substances are represented either by minus sign or a small l is written before their name, and the angle of rotation is represented by alpha. So, rotation of any substance can be written as plus or minus, and then the number of degrees by which the plane of plane polarized light has been rotated. This is the instrument that is used for measuring the optical activity of different substances. We call it polarimeter. It is in a sketch diagram for that. This is ordinary light, that is a light source where vibrations are in all planes. It is passed through a polarizer, which is generally a nickel prism. After that, we have vibrations in one plane only, that is we get plane polarized light. This plane polarized light is passed through this tube which contains the compound either as liquid or its solution, and then after that, when this plane polarized light comes out, we measure the angle by which the original plane has been rotated. Now, as I said earlier that the rotation to the plane of plane polarized light is caused by the interaction with substance, molecules of that substance. Each molecule causes a very small amount of rotation to the plane polarized light, and what we observe here is the total amount that has been rotated due to interaction with various molecules. It means the magnitude of this rotation will depend upon that how many molecules have interacted in the path of this plane polarized light inside the tube. More the number of molecules, more will be the rotation observed. It means for the same substance, if we take the solution of different concentrations or we take the tube in different lengths with the same concentration, the value of alpha will be different. So, in order to have a uniformity so that we can compare the optical activity of different substances, we define a term which we call as specific rotation. Specific rotation is defined as that it is the angle of rotation in degrees of the plane of polarization when plane polarized light passes through 1 decimeter long tube containing this substance in solution at a concentration of 1 gram per milliliter in a polarimeter. Mathematically, we can write it like this, that alpha written in the square brackets. Alpha is the observed rotation, but when we write alpha in square bracket, that represents a specific rotation. This is equal to alpha observed in degrees divided by the length of the tube in decimeter. So, obviously, if it is 1 decimeter tube, it will be 1. Suppose it is a 2 decimeter tube, so L will be equal to 2. So, obviously, specific rotation will be half of the observed rotation, and C represents the concentration in grams per ml. Here this lambda, it represents the wavelength of the light source, because to some extent the rotation also depends upon that what is our light source. So, in order to be very specific, we also specify the wavelength of the light source that we are using, and T represents the temperature at which the measurement has been carried out. So, we try to define all the factors in it. Now, the question comes that why compounds exist as optical isomers. We said that some compounds, they show optical isomerism and they differ in the property that is called optical activity. But why compounds show this isomerism? It is due to chirality in a molecule. Now, what is chirality? The term chirality has been derived from another term called chiral, and the chiral itself is derived from a Greek word care. Care means hands. So, what all it has to do with the hands? Let us first look at our hands. Say this is our left hand. Then if we see it across a mirror, we see its mirror image which is exactly like our right hand. You can compare your two hands, they will be exactly similar. Each of the hand is made up of this one palm, one thumb and 4 fingers. Similarly here, one palm, one thumb and 4 fingers. So, they are made up of identical parts. Here we have shown the mirror image of the left hand, or we can also say this is the mirror image of right hand. Now, let us try to superimpose these two hands in order to check whether they are identical or not. What we observe? We observe that two hands cannot be superimposed, because the thumb for one hand is in this direction, where the thumb for another hand is in this direction. So, they are not superimposable, means what we observe, our two hands, although they are identical, but they are non superimposable. So, this property was given the name as handedness or chirality. So, chirality is a property that when there are two substances which are made up of identical parts, but they are not superimposable on each other. So, the objects which cannot be superimposed on their mirror images, they are called chiral. We have one example as our hands, even gloves can be chiral, or simply the letter P of the English alphabet. If we see its mirror image and if we try to pick this P and put it over this P without changing the plane, means just shifting it from here to here, we find that it is not superimposable. So, it means this letter P of English alphabet is a chiral. Similarly, we can have many chiral objects in our routine life. Let us talk about some objects which can be superimposable. They are called achiral. One example, like chair of this type. There is a chair and then its mirror image. If I take this mirror image and put it over it, it will be exactly superimposable. So, this chair is achiral. Similarly, let us have the alphabet A from English, this A and its mirror image. If I now shift this A over it, it will be exactly superimposable. We can have another example like a butterfly and its mirror image. Because it is symmetrical, we find that this mirror image butterfly is superimposable over it. So, such compounds which can be superimposed over each other are called achiral. Now, let us look for this concept in our organic molecules, and our simplest molecule is methane. The carbon with 4 hydrogens attached to it, they are arranged tetrahedrally. Now, let us have its mirror image. So, this is the mirror image of this molecule. Now, if I put this molecule over it, I see that it will be exactly superimposable, because this hydrogen comes over this hydrogen goes over this hydrogen which is going behind comes over this hydrogen, and this hydrogen comes over this. So, molecule of methane and its mirror image are superimposable. It means methane is achiral. Let us take up another molecule, bromomethane, in which one of the hydrogen has been replaced by bromine in methane molecule. So, this is bromomethane, this is its mirror image. Let us see whether these are superimposable or not. So, this is bromomethane, this is its mirror image. Let us try to superimpose the two. And what we find? We find that this is exactly superimposed over the original molecule. It means the mirror image is superimposable, hence the molecule is achiral, and it does not show optical isomerism, because we said earlier that for a molecule to show optical isomerism, chirality is required. Let us take another molecule, bromochloromethane, in which 2 hydrogen atoms of methane have been substituted, one by bromine and another by chlorine, and this is its mirror image. Let us check their superimposability. This is our original molecule, this is its mirror image. Again, what we find, that this molecule has superimposed over our original molecule, means the mirror image is superimposable, and hence this molecule is also achiral, and it also does not show optical isomerism. Now, let us take up another molecule, Bromochlorofluoromethane. In this, 3 hydrogen atoms of methane have been substituted, one by bromine, another by chlorine, and third by fluorine. This is its mirror image. This is our original molecule, this is its mirror image. let us check their superimposability. What we find here? We find that now this is not superimposable over the original molecule. This part and this part, that is bromine and chlorine, have superimposed, but hydrogen and fluorine, they are not superimposable. It means this molecule and its mirror image, they are different compound, they are not identical. Non superimposable mirror images, hence it is chiral. Means it is due to chirality of this molecule that this exists in two different forms or as two different molecules, but they have the same formula, Bromochlorofluoromethane. So, where do they differ? They differ only in the arrangement of atoms in space, that is in their spatial arrangement. They differ in their configuration. We have already defined the term configuration in our previous session. Means these are the two isomers which have different configuration and they represent a pair of isomers called optical isomers. So, we can say now that chirality, which is non superimposability of mirror images, it is a necessary and sufficient condition for a molecule to show optical activity and hence optical isomerism. If two such compounds they do not exist, then optical isomerism does not exist and they will also be optically inactive. Optical activity is shown only if there are two non superimposable molecules, because one will be dextrorotatory, other is levorotatory. Let us come back to this molecule again, bromochlorofluoroethane. What is so special in this molecule that its mirror image is not superimposable over it? This molecule has one carbon atom which is attached to four different groups, whereas in case of methane, bromomethane and bromochloromethane, all the four groups were not different, they had some common groups in them. Second, such a carbon atom which contains four different groups attached to it, it is known as asymmetric carbon atom. Now, you may find in some places that this is also called as chiral carbon atom. I would like to specify here that overall a molecule can be chiral, an atom cannot be chiral. So, it is not correct to say chiral carbon, this molecule is chiral overall, but sometimes we use this term as chiral carbon when we have to differentiate it from other atoms like nitrogen or phosphorus etc. are there in molecule, then we use this term chiral carbon, but overall for molecule we must use chiral molecule. It is this carbon which has got four groups attached to it and it is this arrangement that has given rise to the optical isomerism, or you can say stereochemistry in this molecule. So, this is also called as stereogenic center. This is another term which is used, stereogenic center, because it is this center due to which stereochemistry in this molecule is originating. A molecule which possesses a symmetric carbon atom like this, it can exist in two optical active isomers, one will be dextrorotatory and other will be levorotatory. You see, this is a molecule in which carbon has got four different groups attached to it and we have its mirror image. We will find that this mirror image is non superimposable over it, as we have seen earlier for bromochlorofluoromethane molecule. So, this is a pair of isomers which are non superimposable over each other, and such a pair of isomers they are called enantiomers. These two isomers, they will have all their physical and chemical properties which are identical, but they will differ in one property, that is their optical activity. One of these isomers will be dextrorotatory, then other will be levorotatory, and the magnitude of rotation will be exactly same. Why this magnitude of rotation is exactly same? Because the optical activity is observed due to interaction of the molecule with the plane polarized light. Since these two molecules are mirror image of each other, they also interact with this plane polarized light in just opposite way, but magnitude remains the same because the substituents are exactly the same. The electronic field which is there, which that is same for both the molecules. So, what we observe, that net resultant observed for optical activity is same in opposite direction. Let us look at the other characters of these enantiomers. Enantiomers are not superimposable on their mirror images. One of the isomer will obviously be dextrorotatory and other is levorotatory with the same magnitude. They will have all other physical and chemical properties which are identical. Now, what will happen if we take mixture of two enantiomers? Mixture of two enantiomers in the same ratio is known as racemic mixture. Racemic mixture will be optically inactive. That is, when we put in a polarimeter 50-50 ratio of two enantiomers, the net resultant will be 0. The obvious reason is that what happens, each enantiomer rotates the plane of plane polarized light in equal and opposite direction and they cancel each other's effect like this. This ordinary light pass through polarizer becomes plane polarized light. Now, let us say it is a solution of one compound, it rotates by some angle, it is a solution of second enantiomer which rotates this light by the same magnitude in opposite direction. So, net resultant will be just like our starting position. Actually, the two solutions are not kept separately. When we have the mixture of two enantiomers in the tube, so our light will encounter this type of molecule as well as this type of molecule, they will have their equal and opposite effect and net resultant will be 0 optical activity. The cause for optical inactivity of enantiomers in racemic mixture is said to be external compensation, because the effect produced by one type of enantiomer is externally compensated by another enantiomer. So, today we have discussed that optical isomerism exists in molecules due to chirality, and chirality is a property of non-superimposable of mirror images. So, today we first reviewed the work of our previous session and then we moved on to optical isomerism. We discussed that optical isomerism and optical activity in molecules is due to a property called chirality. Chirality means non-superimposability of the mirror images over each other. The optical activity is measured with the help of an instrument which is called polarimeter. Polarimeter involves the use of plane polarized light. This optical activity and optical isomerism is due to chirality. Chirality means handedness or non-superimposability of mirror images over each other. Then we talked about enantiomers and racemic mixture. So, we discussed that compounds which are chiral, they exist as optical isomers which are called enantiomers. Now, here one more thing I would like to specify, that today we had taken the example which had only one asymmetric carbon atom and there are two isomers which are possible, one we draw as the initial compound and second at its mirror image. But if a compound has got more than one asymmetric carbon atoms, then number of isomers will be much more, and that we will be discussing in our next session, that if a molecule has got two asymmetric carbon atoms or three asymmetric carbon atoms, then how many optical isomers are possible, and we will find that some of these may be even optically inactive. But the cause of optical inactivity there and the cause of optical inactivity of racemic mixture is different. Racemic mixtures, they become optically inactive because in the mixture the two compounds are there which are rotating the plane of plane polarized light in opposite direction by the same magnitude. So, in our next session we shall discuss further about the optical assays.